Welcome, friends. In the last session, we have seen the SAG, definition of SAG, and influential parameters of SAG calculation. Now, in this part of the lecture, we shall see the mathematical description of the SAG, means how the weight of the conductor is related. We know that it is related in direct proportion, but whether it is in truly direct proportion or the square of the direct proportion, we shall see, or we shall investigate all these facts. Okay, so let us proceed. Let us consider this figure 2. Okay. We have a conductor POQ. Okay, POQ is the conductor, right? This is the conductor POQ, and O is the minimum point. O is this minimum point, and this D is the sag. Now let us consider this is the span length P between P and Q. So P is the tip of one tower, and this Q point is the tip of the another tower. So the length between two towers is L, which is called span length. Now the conductor length, that is POQ, this conductor length, total length is L. So if we divide, now first of all, let me discuss, or let me tell you that we are first calculating sag provided these two towers are at same level. That means if this is the land, towers are at same level. That means the tip of the vertical distance of P and Q from the ground are same. So that is why it is called towers at same level. So for this type of case, POQ, let us the total conductor length is L, and from P to O up to this, it is L by 2. It is L by 2. So P to O, and then from O to Q, it is L by 2. That is the half of the conductor length. So there is a difference between small n and capital L. Capital L is span length, which is the length between two towers. However, small l is the conductor length. Small l is the conductor length. Okay. Now we consider any point R on the length of the conductor. We consider any point R on along the length of the conductor. So at this point R, tensile strength acting is T. And its horizontal component is Tx, and its vertical component is Ty, and this angle is theta. Now there are three fundamental forces acting on this diagram, on the figure 2. First of all, at this point H is acting. So this is H, tensile strength. This H is balanced by this Tx, that is the horizontal component of tensile strength. So H is balanced by Tx, that is equation number 1. I have already mentioned that weight of the conductor to be taken in kg per meter. And sag is D. That means this length, vertical distance. And the first what I have told you, that is this tensile force, this H is balanced by this Tx, right? So H Tx is equal to H, which is equation 1. And similarly, this let us say this distance, that means from O to R, any distance which is S actually. So the total weight of this conductor is Ws. Total weight of this conductor, that means weight of the conductor we have assumed W kg per meter. Now if I consider a section of length S, that means from O to R. O to R, it is only S meter. So the total weight of this section, that means total weight of the conductor up to section O to R is how much? W into S. And that is acting vertically downward at the midpoint of the conductor. At the midpoint of the conductor, at this point, it is the midpoint of the conductor. So this Ws will be balanced by this Ty. Ws will be balanced by this Ty, that is equation 2. And now if we say, that is if due to the temperature variation, if a very small change is occurred, ds, very small change in length occurs due to the temperature variation, and then this, due to this change of dx, an elementary change will occur along x direction, which is dx, and elementary change will be occurred along y direction as well, which is dy. So we can say that is dy by dx, we can say dy by dx, we can say dy by dx, which is equal to nothing but ty by tx, which is nothing but ty by tx, and which is equal to, that is from equation 1 and 2, from 1 and 2 we can say Ty is equal to Ws and Tx is equal to H. So dy by dx is equal to Ws by H. So this is equation 3. Now from this diagram, from this triangle, equilateral triangle, right angle triangle, we can write ds square is equal to dx square plus dy square. So if you take from there, if you take ds by dx whole square, that will be equal to 1 plus dy by dx whole square. Now what is dy by dx? Dy by dx is equal to Ws by H. So we can write ds, that is equal to dx into under 1 plus Ws by H whole square. So from there dx is equal to written by ds by this entire term 1 plus Ws square plus a square H square. So this is equation number 4. Right, this equation. So now if we go conducting an integration of this equation 4, we shall get this solution. We shall get this solution. X is equal to we shall get this solution. What is that? It is written x is equal to h by w sine hyperbolic inverse Ws by h, and we have a constant of integration, that is k. Where k is a constant, it is given. Now from figure 2, if let us say this point is origin, that is at this point x is equal to 0, y is equal to 0. So that is why we have written, so at x equal to 0, s will be also equal to 0, because at this point everything is 0, because it is point of origin. So at this point x is equal to 0, so this distance is 0 here, so s is equal to 0. So if we substitute here x is equal to 0 and s equal to 0, so if we put we will get a value of k is equal to 0. So from there, this equation turns out to be x is equal to h by w sine hyperbolic inverse w into s by h. So this is the equation of 6. This is equation number 6. Now again we are putting when x equal to L by 2, s is equal to L by 2. That means at this point, at Q we have x is equal to L by 2. So from, if we measure from here, so this length is L by 2, capital L by 2, and conductor length is also small L by 2. So at Q x is equal to capital L by 2 and s is equal to small l by 2. So we shall substitute that in this equation. So if we substitute x is equal to L by 2, if we substitute x is equal to L by 2 here, and s is equal to, x is equal to capital L by 2 and s is equal to small l by 2. So we shall get an equation like this, and from there we shall get small l is equal to 2h by w sine hyperbolic wl by 2h. This is equation number 7. So from equation number 7, if we expand, we shall get this form. So L is equal to 2h by w, it is kept outside. Now if we expand sine hyperbolic, so we first term we should get 1 by 1 factorial wl by 2h. Then next term 1 by 3 factorial plus wl by 2h whole cube, and so on. So if we neglecting higher order terms, we don't require them. If we neglecting higher order terms, then you should get from there L is equal to, if you take L outside common, then 1 plus w square L square by 24 h square. Now if we utilizing equation 3 and 5, so this equation, not this equation, dx dy by dx is equal to ws by h, and equation 5 x is equal to this, we shall get dy by dx, that is ws by h, which is equal to sine hyperbolic wx by h. So from there we can get dy is equal to sine hyperbolic wx by h dx. So now if we integrate equation 8, we shall get a solution of this. Y is equal to h by w cos hyperbolic wx by h plus k1, where k1 is the constant of integration. Now how should you get it? We should get by putting x is equal to 0 at y is equal to 0. So from equation 9, from this equation, if we put y is equal to 0 and if we put x equal to 0, so we should get this one as k1 as minus h by w. So if you substitute, y should be is equal to, from this equation, y should be is equal to h by w within third bracket cos hyperbolic wx by h minus 1. So now this is equation number 10. So if you substitute, or if you expand this, it should be h by w, it is outside, then if you expand cos hyperbolic, it should be the first term will be 1 and the second term will be 1 by 2 factorial wx by h whole square. Then next term will be 1 by 4 factorial wx by h to the power 4 and so on. And thereafter this minus 1 term. So if we neglect all these terms, so just we are taking this term, so this 1 and 1 getting cancelled, so it will be y is equal to h by w, y is equal to h by w into w square x square by 2h square. So from there we will get y is equal to w x square by 2h. Now from figure 2, this figure we shall get what? This expression, that is t square is equal to tx square plus ty square, this right angle triangle. This right angle triangle we shall write what? We can write, you see, t is equal to, that means t square is equal to tx square plus txy square. What is tx? It is h square. What is ty? It is w square plus h square. So if we take h common, so we should have a relation t is equal to h, t is equal to h over cos hyperbolic wx by h. So if we now substitute or if we now expand cos hyperbolic, the first term is 1, second term is 1 by 2 factorial, third term is 1 by 4 factorial in this way. So if we neglect the higher order terms, we should get x is equal to capital L by 2 and y is equal to d. So from there we should get a relation w is equal to d is equal to, that means sag d is equal to w L square by 8h. So this is our relation. So what intuitively, so this result is very important. The derivation might not be useful for you, but this relation is very important, that is the sag, maximum sag WL square by 8h. You see, intuitively what we have observed previously, that sag is dependent on 3 parameters. Sag is dependent on 3 parameters. First of all, it is directly related with the weight. Secondly, it is the directly related with the L, and it is inversely related with the tensile strength or H, whatever. Now the mathematical expression says that it is okay, it is perfectly alright, it is directly related with W, fine. However, it is, as far as the length is concerned, it is direct, it obeys the direct relation, but is this a square relation is there, okay, and by h, so it is also working. So mathematically sag is related with WL square by 8h at this point, maximum sag. Now this expression is also important, that is this expression y is equal to wx square by 2h, y is equal to wx square by 2h. You see this equation 11. It is required to determine the sag at any point. This is determine the sag at any point, right? So this equation 11 is very important to determine the sag at any point. Let us say we have the second case, that is we need to calculate sag. We need to calculate sag. We need to calculate sag. However, now consider towers at different levels. Now consider towers are at different level, like in hilly areas what we have observed. Suppose one tower is at this place, another tower is this place. So conductor is taking this shape. So towers are at this is actually practical scenario in hilly areas, right? So this is the diagram for you, that is let us say this is the tip of the first tower point P, and point Q is the tip of the second tower Q, and the span length between two tower is L, it is same. However, now the point of the maximum sag is not at the midpoint, it is at some distance x1 from tower P and from distance x2 from tower Q. So x1, naturally x1 plus x2 will be is equal to capital L. Capital L, they are not equal. Okay. So we need to determine. So what will be x1 and what will be x2. Also from tower P, that is tower 1, that is this sag is D1, and from tower 2, that is point Q, sag is D2. So we shall see what are the relation. So as I mentioned already, x1 plus x2 is equal to L. So from this expression we can write, that is the sag D1. Sag D1, that will be equal to W. Now x here x1 square, x here x1 square by 2h. Similarly, the sag D2 we can write D2 is equal to W x2 square by 2h. So now this height, the difference in height is h. H is nothing but D2 minus D1, that is difference in sag. So if you subtract these two formulas, or these two D2 and D1, we shall get a relation of this. So we can easily find out x1 is equal to capital L2 minus H capital H 2L, and x2 is equal to capital L by 2 minus, or sorry, for x2 will be plus H capital H by WL. Now in some literature you can find this H, they have used T. Both are same, you can use any one. Okay, you can use any one. Now without proceeding further, that means effect of ice, I shall quickly go take you through a problem. What is the statement of the problem? A transmission line conductor consists of a hard drawn copper of 225 square mm cross section. That means cross sectional area is 225 square mm, and the span length of 160 meter. So L is 160 meter here. The conductor has an ultimate tensile strength of 49.3 kg per mm square, and allowable tension is not to exceed 1/5 of the ultimate strength. That means, okay, now let us first determine total tensile strength. You see this value, the conductor has an ultimate strength of 49.3 kg per mm square. That means what? For a cross-sectional area of 1 mm square, the total tensile strength is 49.3. However, it has a total area of 225 square. So total tensile strength, that means ultimate tensile strength into cross-sectional area of the conduct, that means 49.3, which is the ultimate tensile strength, this value into total cross-sectional area, which is found to be 11,092.5 kg. Now this statement is very important. Allowable tension is not to exceed 1/5. That means the allowable tensile strength, that means 1/5 means 0.2. So 0.2 of this value will be 2218.5 kg. That is the allowable, right? Now if we go proceed further, now weight of the conductor, now let us say determine the sag. Now you need to calculate, determine the sag. Now this information is important, that specific gravity of the hard drawn copper is 8.9 gram per cc. This data is very important. The specific gravity. So weight of the conductor per meter length, that means kg per meter. How we will get? We should multiply specific gravity of the copper into volume of the conductor. That means volume of the conductor for 1 meter length. So specific gravity is 8.9 gram per cc and area is 225 by 1000 centimeter square. That means 225 given in millimeter square. So if it needs to be converted into centimeter square, it should be divided by 100. Now into 100 centimeter you need to multiply, you need to count this for the entire length. So it will be coming around 2.0025 kg per meter. 2.0025 kg per meter. That means you see why this 100 centimeter, because the weight of conductor you should consider it is kg per meter. Now if you go through this, it is gram per cc, that means cubic centimeter, we have a centimeter square. So in the denominator we have a extra centimeter. So you need to multiply this with 100 centimeter, that means 1 meter is called 100 centimeter. So that is why it is come in kg per meter. So we have all the data. So D is equal to, that is tensile strength, which is this value, that is weight of the conductor 2.0025, that multiplied with span length L square, which is 160 meter, divided by tensile strength, that is the allowable tensile strength, that is 8H2218.5, this value. So it will be found to be 108.3 centimeter. This is the sag. Now we will take you through the second problem. Now the rest of the problem is consider the cases of ice and wind. I'll coming later on. Now let us consider the second problem. Let us consider the second problem. Now two towers, height 32 meter and 48 meter, support a transmission line conductor at water crossing. Let us say this is a river. This is the river. So from the river we have a conductor which is 32 meter and 48 meter support. Now at the last line, assume bases of the towers be at water level. Okay, so this is the this entire length is nothing but the height of the tower, that is 32 meter. And this is 48 meter. This is the water base, so height of the tower is 32 meter. So this distance is not 32 meter, I think it is 16 meter. So the difference. Now the horizontal distance between the tower is 288 meter. So this distance are 288 meter. Now next, coming to the data, if the tension in the conductor is 1485 kg, find the clearance of the conductor at a point midway between the support. Let us say this is the midpoint, although it is not in scale. Let us say point X is the midpoint. Okay, this is the midpoint. Although it is not in scale, but for the time being, please consider. Find the clearance of the conductor at a point midway between the support. Weight of the conductor is 0.86 kg per meter. Now how should solve? So you see, this is H, this is H. This should be 48 minus 32 is equal to 16 meters. So this is wrong. Actually, I have done a mistake. It is 16 meter. Now from the formula x1 is given by L by 2. First you have L by 2. What is L? L is 288. 288 by 2 minus what is h? Small h is nothing but this height, that is 32. Sorry, not 32, it is 16. 16. Capital H is 1485. 16 into 1485 divided by what else? It is L by 2 WL. What is W? W is 0.86 kg per meter into L. L is 288. So if you solve this, it is given by 48.1 meter. 48.1 meter. So this distance is basically 48.1 meter. So now if we evaluate x2, the everything will be same. Only difference is this symbol is plus. 16 into 1485 divided by 0.86 into 288, which is equal to 239.9. So basically this distance is from this O point to this distance is 239.9 meter. Okay, now sag at midpoint. Now we need to calculate the point, find the clearance of the conductor at the point midway. So you need to find out the sag. What is the sag? So how you calculate? That means if you see, if this is the midpoint, then this length is 144 meter, and this is nothing but this 239.9 minus 144. So this length is nothing but 239.9 minus 144 meter. Okay. Maximum sag. So D2 we have calculated. Also D1 we have calculated. So this D2 we have calculated, which is 16.66. This is the maximum sag D2. And D1 we have also calculated, which is 0.7 meter. Now from the figure it is clear that midway, that means this midway, the clearance should be, you see. And now this is 2.66, this distance 2.66. How? So I think I have missed that. It is 2.66. So that means it is at the midpoint. So let us say that sag is y. So y is WL square. That is W means you know how much? It is 0.86 kg per meter. 0.86 kg per meter into L. So now the distance is, you know, it is 144. It is 144 divided by 2 into L. Sorry, 2 into H. H is this value 1485. If you solve this, I think you should get this to be as 2.66 meter. So if this is 2.66 meter now, from this water base, that is the river bed, to this height is 32 meter, and this sag is 0.7, so this must be 31.33 meter or 31.3 meter. So 31.3 plus this 2.66, it is the minimum clearance at the midway. 31.33 plus 2.67, which is equal to around 34 meter, is the midway. I repeat, this D1 is 0.7 meter. D1 is 0.7 meter. D1 is 0.7 meter obtained. And distance from the water base to this point P, it is 32 meter. So if I assume this point is P, this water base is, let us say, X, or some other, let us say this is A, and let us say this point. So these points are same, basically O. So OA, that means PO is 0.7. PO is 0.7 meter, and AP is, AP, this total length is 32 meter. So if you subtract this, so we shall get that the clearance from the river surface to this point O is nothing but 32 minus 0.7, which is equal to 31.3. So if you add this 31.3 with this 2.66 meter, 2.66 meter or 2.67 meter, so you will get the total clearance at the midway. Total ground clearance at the midway, which is equal to 31.3 plus 2.67 or 7, whatever. So roughly you will get 34 meters. So this distance is basically, this clearance is nothing but it is 34 meter. This is the answer. So with this, we shall end here this part. In the next part, we shall see the effect of ice and wind flow with a numerical problem. Thank you.